Good morning, distance students. I turn off the microphone here, so if you have a question, please raise your hand so I know you have a question, and I will turn on the microphone for you. You can ask your question. Now, do you have any questions before we get started the lecture? Any question? Great, thank you. So, let's start the lecture by talking about more about the op-amps. And so we talk about the op-amp. The ideal op-amp has infinite input resistance, infinite gain, zero output resistance, right? That was the characteristic. And infinite gain. Now, to control that gain, we need to add a couple of resistors here. If you add this couple of resistors into the circuit, right now your amplifier is not just that part. Your amplifier is the whole thing. That's your amplifier. This is coming input. That's the output. That's the whole amplifier. To analyze op-amp, we use 4 rules. First, whatever the voltage at the plus pin is, its voltage is going to be same as the negative. No current goes to op-amp. And we're going to use the Ohm's law to find what is I1. And the I1 has to be the same as I2. Why? If the current coming to the node has to get out. And if it's not going to op-amp, so where it goes? Has to go through R2. We wrote the equation and we find out that VO over VI for this circuit is minus R2 over R1. And we call this one inverting amplifier. What does it mean, inverting amplifier? Yes. That's exactly correct. So what it is if your input is a sine wave like this, your output is exactly opposite. Your output is like that. That's the reason we call it the inverting amplifier. Now I have a question for you. Things change. What is the input resistance of this amplifier? Input resistance of this amplifier. What is it? Yes. Why? I have a couple of options for you. One is infinite. Second is R1. Third, R2. Fourth, R1 plus R2. Which one is correct? How many of you think is infinite? How many of you think is R1? Raise your hand. Yes. So your input resistance is, and how do we know that? To answer this question, for any circuit, if you don't know what is the input resistance, all we do is we're going to add a test source. In this case is the VI. We're going to calculate what is I1 or the current coming from that. Your R-Thevenin is VI divided by I1. In this case is correct, is R1. Now I want to trick you guys. If I put the input on the plus pin, right? Same circuit. If I put the VI on the plus pin, which make it a non-inverting amplifier, what would be the input resistance? Same thing, R1? Infinite? Infinite? You said infinite? It's correct. Yes, infinite. So if the input is on the plus sign, your input resistance is infinite. Why? If I have a source here, what is the current coming out of that source? Zero, because there is no current going to go through the op-amp. If it's zero, you have VI divided by zero, your input resistance is infinite. In this case, it's R1. And you know, these equations are correct not only for resistance. So if I have this circuit, a capacitor, exactly the same process, same equations, nothing changed. The only thing is changing is that C, the impedance is minus J divided by omega C. Let me clean here. And VO over VI minus, before was R2 over R1, right now is minus J divided by omega C divided by R1, and the answer is J divided by omega C R1. That's your gain. So this equation also works if you have impedance. Any question? Okay, if you don't have question, help me out solve this problem, right? Grab your calculator, write down the problem, and this problem helps you to do the first project. The problem is, let's say I have input VI, R1, R2, VO. So the problem is design so such that your gain is minus 25. Your maximum I means drawn from the source, we would like to be less than 10 microamp. What I'm looking for is what would be R1 and R2. What would be the range of VO if VI is changing minus 25 millivolt to 25 millivolt? Where to start? What is the gain of this equation? One more time. Help me out write the equation. What's the gain? Correct. Minus R2 over R1, and we want to be minus 25. Okay. Can I pick any R1 or R2 to satisfy this equation? Yes? Any R1, any R2. So what is my limitation? Why I cannot pick any number? Yeah, excellent. So max current has to be less than 10 microamp. We know the I equals VI divided by R1. You want this to be 10 microamp. VI here is 25 millivolts. So your R1 is 25 millivolts divided by 10 microamp. and that will give you a limit of 2.5K. Your R2 has to be 25 times multiply this, so it's gain multiply 2.5, and this is 62. Now, if you want to find the range of VO, VO basically is 25 multiply the input. So 25 multiply 25 millivolts. 25 minus 25 millivolts, which is VO 625 millivolts minus 625 millivolts. So in this example, the only thing limits us to not to pick any number for R1 and R2 was the maximum current drawn from the source, right? What are the other limitations? Sometimes I'm asking you, I want the input resistance to not to be less than that number. That's another limitation. Sometimes, if the gain is high, and let's say same problem, let's say we ended up with the R1 of 10K, and your gain is 100. What R2 should be? Your gain is 100, your R1 is 10K. What is the R2? What's that? 1 mega ohm. Is that acceptable? No. 1 mega ohm creates a lot of noise, so you don't have that fantasy of having a large resistor as well. So what is the solution? Solution is, we call it the T network. Instead of have a basic amplifier with 2 resistors, right now I have 4 resistors with this configuration, and let's see how it works. So the I1 for this problem is right down here. The I1 basically is VI divided by R1. I4 is minus Vx divided by R4. I3 is Vx minus Vo divided by R3. I2 minus Vx divided by R2, which has to be the same as I1, and the I1, we ended up with the first equation, Vi divided by R1. This guy gives you Vx equal minus R2 over R1 multiply Vi. And if you replace this one back into the third equation, so we had I2 for I3 equals I4 plus I2. If you just replace by those terms, you're going to have Vx minus Vo divided by R3 minus Vx divided by R4. That's your R4. Minus Vx divided by R2. And that's your I2. Summarize it, get rid of and replace the Vx by this one. This is the result. The result is AV, which is the VO over VI minus R2 over R1 1 plus R3 over R4 over R2. That's your gain equation. I want to ask you a question. I want to know if you understand or not. What was the problem with the simple inverting amplifier? What was the problem? Why we can't always use just the simple inverting amplifier? Why? Yes? Okay, one more time I tell you guys. Yes, Richard, your answer is correct. But let me put it this way. We said non-inverting amplifier works fine. It's good. It's only 2 resistor, 1 op amp, you are done. You can amplify any signal. But if your gain is too high and you want to have a high input resistance, R1 high, you're going to end up with a large R2, right? Large R2 generate noise in the circuit. So if you're an electronic designer, you don't want to use 5 mega ohm, 10 mega ohm, 2 mega ohm, no. This resistor over a 500K, they start generate noise in the circuit. If you have a bunch of them, then the circuit is noisy. What is the solution? The solution is the T network. You are adding 2 resistors into it. You're going to get a little bit more complicated equation, right? Let's give one example and see how it works. I'm asking you, and I don't say what kind of amplifier you use. I'm asking you, hey, I need design an amplifier with a gain of minus 75. We would like to have input resistance of minimum 20K. And no resistance, no R has to be greater than 200K. That's your specification. That's the spec. The first thing is I will check if I can design this with 2 resistors because I don't want to have extra components. So approach 1. I'm going to put 20K here because input resistance has to be 20K. I need to choose R2. Now you guys tell me what R2 I need here. Yeah. Excellent. So 75 multiplied 20K is 1.5 mega. Are we fine? Design is good? No, because we said, hey, no any resistor greater than 200K. So this method is not going to work. Okay, approach 2, we're going to use the T network. And I have that equation there. Input resistance is exactly the same as before. So let's have minus 75 this side. R2. What has to be R1? What is the R1 here? 20K. Okay. 1 plus R3 R4 plus R3 over R2. I have 3 resistors to pick. This is what I'm going to do. I will choose that ratio to be 8, that ratio to be 8, that ratio to be 1. Right? So the gain, let me just make it this way. Let's say the gain greater than 75. You want this to be greater than 75, and that perfectly satisfies the condition. Is that correct? Right? Okay. If I want that ratio to be in, so your R2 has to be 160K. Let's have R4 20K. That makes your R3 again 160K. And 160K over 160K is 1. Your gain with this condition is going to be 80. And guess what? There is no any resistor over 160. Right? Get the point? If you ended up in your design that you have a really large resistor there, it's not working, all you need is to use the T-network. Question? Yes. You asked a good question, and part of the objective of an electronic designer is to know what parameter, if it's higher, is better, what parameter has to be lower. This is the part of the learning in this class for you, right? So for the gain, you don't want to be lower than what you design. For sure, no lower. Higher is a little bit okay. Why? Whenever you design something on the paper with the gain of 75, there is no way in the lab you get 75. Probably you're going to get 70 because nothing is ideal. The resistors are not ideal. Op-amp is not ideal. Your gain is going to be lower. If I design the circuit with those values, hopefully I get 75 in the lab. So for the gain, always shoot for a little bit higher. Don't shoot for 200. You don't need that gain. That's going to saturate the next stage and causing problems. A little bit higher is fine. There are some other parameters when we go through the course. You need to think of, okay, I don't want this to be that high. I'm going to shoot for lower. So understanding what is the limit, what is good to be a little bit higher is. In this case, is not 75, but I made everything to be greater than 75 to make it correct, right? I made here AV gain greater than 75. So in this case, the gain is 80, and I think it's fine. If you're a little bit over that, that's fine. Okay. Next topic is, I'm going to write one more time. Here is R2, here is R1. Input, VO output. One more time, what is the gain of this equation? This equation is correct only in this condition. If if the gain of the amplifier itself is infinite. If the gain of amplifier is infinite, this equation is correct. However, the gain is not exactly correct. The actual equation would be like this. And AOD is the gain of op-amp itself. It's called the open loop gain. So for example, if you have a gain of minus 10, and if your R1 is 10K, your R2 has to be what number? 100K, right? Now this table shows if your AOD is infinite, yes, you're going to get a gain of 10. If your AOD or open loop gain gets to only 100, you're not going to have a gain of 10, you have a gain of 9. So the higher the gain, you're going to get closer to that number. Question? Okay. Next is the summing amplifier. In electronics, sometimes we need to add some signals together. This circuit exactly do the job. All you need to do is using the superposition. If I use the well, same rules by the way. So if here is the 0 volts, that point is a 0 volts, and no current goes to op-amp, so your I1 in this case is VI1 divided by R1. Your I2 is VI2 divided by R2. I3 VI3 divided by R3. And we already know the I4 is the summation of all this current and your I4 basically is minus VO divided by RF. If you replace everything in that equation, you're going to get the gain equation, and your gain equation is minus RF multiply VI1 divided by R1 plus divided by R2 3. For example, let's do one example here. 10K, 10K. We're going to sum up these two signals, pass it through an op-amp, and here is 40K. The input signals, one of them is the AC. It's an AC, it's minus 0.5 sine of omega t. The second one is DC plus 1.2. You already know your gain of this equation is minus 40 divided by 10, and 1.2 minus 0.5 sine of omega t, which makes your VO minus 4.8 plus 2 sine of omega t. Okay. This is actually a summing amplifier or using an inverting amplifier because the concept is still is the inverting. We do have a summing using non-inverting amplifier, which we're going to get to it soon. Question. Did I tell you guys that if you ask a question, you're going to get more credit for it? You know that, right? Okay. So stop me if anything is wrong or is anything confusing. So non-inverting amplifier, what's happening is you're connecting your source to the non-inverting pin or the positive pin right here. How do we analyze this circuit? Same rules. Before we said the point 1 is 0. Right now the point 1 is not 0. What is the point 1 voltage? Exactly. So right now we know the VI, V1 equals the V2 is equals the VI. So this point is VI. Let's do the Ohm's law. What is the current going through the R1 through that direction? Tell me. No, the current going that direction. Excellent. So I1 is one side of the any resistor, 0, minus the voltage the other side, in this case is VI, divided by R1. What is the current going through the R2? Voltage in the other side is VI, the other side is VO divided by R2. We know the I1 has to be the same as I2. So you're going to get your gain equation minus VI divided by R2, VI divided by R2 of I1, right? The gain equation is 1 plus R2 over R1 VI. As you can see, there is no positive, negative sign here. It's called non-inverting. There is no phase shift between input and output. I want to ask you a question. What is the input resistance now?
Infinite.
That's correct, yes. So the input resistance is infinite. Yes, go ahead.
Can you also use 2 op amps to invert the signal from instead of using that?
Yeah. Yeah. You can have 2 inverting op amp back to back in series, which is going to make the signal positive. Yes. So I personally, I won't use a non-inverting amplifier that much in the designing, because anytime I use positive pin, there is a good chance of the feedback to be high or the circuit is not working. Sometimes you make it work. It's not but what is the application? of this guy is called the voltage follower. When you do not have R1 here, and your R2 is just piece of wire. Can someone tell me what's the gain equation for voltage follower? VO equals VI. Why do we need to use the op-amp to have two voltages the same? I could originally just have the VI. Yes? Yes? Exactly. Input and output is isolated to each other. Your answer is also correct. Now, let me just give you one example how that might change. Let's say you have a source, voltage source, and you have a RS internal resistance of that source is 100K. Your load is 1K, right? Do you know what is that VI, the voltage of VI to get to the load? What is it? Your VI in this case is, let's use the voltage divider, almost 1%. Only 1% of input voltage gets to your load, right? The rest is going to be consumed or wasted across that 100K. Okay, if I'm using a voltage divider, how that's going to change? No problem. What is the voltage at this point? Is excellent. Yes, so it's going to be VI, same as this one. Why? There is no current go through op-amp. You have no voltage drop across that 100K. If this is the VI, here is VI, here is VI. You're done. Got the point? So you have, in the second case, you have 100% of the input voltage coming to your load. First one, you only get 1% of it. So voltage follower is correct. It's just isolate output and input. We also can have a summing using a non-inverting amplifier. I want to start with an example. There are the shakers. You know what? Oh boy. No, when I got to the class, the screen was on, right? This screen cannot be on more than maybe 1 hour and a half or 2 hours. After 1 or 2 hours, they turn off to be cool for like a few seconds or something. I can turn it on in a minute. Just give me a second. If you already have in your note, why don't you, this is on you, I want you to solve it and tell me the gain equation. If not, it's coming up in a minute on the screen. Yeah, everything is on the toilet. Yes, hold on a second. Okay, gentlemen, ladies, that's your circuit. What I want you to find is what is the VO as a function of VI1 and VI2. use your circuit analysis skills, use that 4 rules we talked about Tuesday, and tell me the function. By the way, I won't be on campus tomorrow, but I'm available by email if you have any questions. And there is no lab tomorrow. Does anybody got a number for me? VO as a function of VI1 and VI2? And VI1? Sure. Anybody got the same answer? So the way to solve the problem is find out what is the voltage here, and all you need to do is the superposition. So first you assume the VI2 is 0. Your VI basically is VI1 multiply 50K if this part is grounded. So it's a voltage divided 50K plus 70 plus 25 plus VI2, now you assume VI1 is grounded, multiply 25 and summation. If you know the VI, now I know the VO is 1 plus R2 over R1 VI. So 1 over 70 divided by 5 multiply VI, and the VI is VI1. 50 divided by 50 plus 25 is 2 over 3rd plus VI2 1/3. That's your answer, right? It's a non-inverting, so you don't have any phase shift problems, or that negative sign is going to go away. You got the same number? So, how many of you guys got the same number or same equation? Okay. So I want you to do this at home. Design a circuit that does this for you. VO equals 6 VI2 plus 3 VI1 plus 9 VI3. You don't see any negative number between those, so it means you are using a summing, non-inverting summing, and all you need to do is you have 3 inputs, find out R1, R2, R3, R4. Okay. Next topic is integrators. Part B of your first project. VO equals 6 VI2 plus 3 VI1 plus 9 VI3. So integrator, probably your math is very good. Whenever we talk about the integrator, some come to your mind, okay, is x, integral of x is half of x squared, right? This is come to your mind. What does it mean, integrator or differentiator in electronics? I don't have something to integrate or numbers or calculator, so what does it mean?
You can integrate current to get charge.
You can integrate the current to be charged by frequency? That integrates the signal. That's correct. So let me just, before we get to this, is if your input is a sine wave, your output is cosine wave. So your output is cosine. Or if your input is a square wave, your output is, so let's say this is VI, your VO is, well, it's a constant, so you're going to get X. Then you have a negative number, so that means you're going to go with the negative slope. Your output is something like this. That means integrator. It's also correct. It means you are integrating charges to get the current. Okay, if you want to design the, so for example, for your project, what I'm expecting to see if your integrator works or not is if your input is a sine wave, your output should have 90-degree phase shift. That means your integrator works correct. So how to analyze this signal is straightforward. Your I1, and let's call this one IC. We know the I1 has to be the same as IC. Your I1 is VI divided by R1. Your IC is C dVC dt. What is this? VC. VC is the voltage, the other side minus this side. So C D0 minus VO over dt, which is minus C dVO over dt. if I integral both sides and just play with those variables, I have minus 1 divided by RC integral of VI dt. Now, if the VI is sine omega t, right? What's the integral of sine omega t? 1 over omega cosine omega t, right? So there is 1 omega t. For your design, all you need is to design R and C based on the omega, and omega comes from your frequency, to make the whole thing to be 1. So the gain has to be 0 dB or just 1. So when the input is 1 volt, I'm expecting to see the output exactly 1 volt, but with a 90-degree phase shift. Question? Okay. Next is differentiator. Same as before, if you have that input, the differentiator of t is 1, so your output is going to be a square wave. And then you say, well, that's I1, I2, so C1 d, instead of 1 d VI over dt, that's your I1, equals minus VO divided by R2, and you can find the gain equation, which is a differentiator, VO minus R2 C1 dVI dt. Same as before, if you have sine of omega t, your output also should be a sinusoidal with 90-degree phase shift. You can analyze either these two circuits using a different method. You could say, well, I don't want to do that integral things. I want to say this is minus j divided by omega c1, and I use just the general, so VO over VI is in general, let's call it the Z2 over Z1 minus Z2 in this case is R2, Z1 in this case is minus J divided by omega C, and that is J3R2. That's your gain too. You can use those equations as well. Okay. Any question regarding integrator differentiator? Next application using the op-amp is current to voltage converter. So current to voltage converter, the goal is we want to have that IF here into a voltage. Now I tell you where is the application of this type of circuit, right? Some of the sensors, they don't generate voltage for you, they generate current. Like what? Like piezo crystal sensor, when you push it, or is a load cell, when you push that crystals together, it's going to generate tiny bit current for you, right? All the electronics, microcontroller, input, oscilloscope, everything works based on the voltage. Somehow you need to convert that tiny current into a voltage. That can be your circuit. For example, how to analyze this, let's say this RS is really a big resistor, and your I1 is the same as IS. If we ignore RS, so this is correct. And how, so we know that I2 is the same as I1, is the same as IS. And we know the I2 is minus VO divided by RS. This side is IS. So your output voltage is proportional to that current. Or in another word, you're converting a current into a voltage. For example, if I say this is a piezoelectric microphone, and when you talk, it's going to generate, let's say, just arbitrary number, 1 microamp, right? If you choose RF 1 megaohm, that one tiny microamp is going to be translated to a 1 volt. Your output, you're reading a 1 volt. Yes? If it's high. If it's not high, it's matter in practice. Why? Because op-amp is not ideal, right? If the op-amp is not ideal and has an input resistance, let's say the input resistance is 2 megaohm. If the RS is also 2 megaohm, you're going to lose half of that current. Make sense? So it's matter as long as it doesn't matter if one more time, what was your question?
What does RS matter?
The resistance seen by that direction is comparable with the RS. Then it's matter. Then any resistance seen by that direction, and that direction is only is your input resistance of the op-amp. So if it matters if your op-amp is not ideal and the value of input resistance is comparable. If it's way more larger, which is the case, so you can ignore it. Right? Another application is voltage to current converters. This has been useful to read the voltage using the analog multimeters. So analog multimeter basically works with this. Why? When you're measuring the voltage, you are seeing an arrow is moving. What moves that is a current. Basically, the current is moving that arrow in there. So one circuit that could do this job is this one. So the whole thing is voltage to current converter. In this case, we know the I1 has to be the same as I2. The I1 is VI divided by R1. And this is the same as I2. So whatever current passing through this or move this arrow is proportional to the input voltage. What's that? This one? It's just a meter. That's why I said the analog multimeter. Do you remember analog multimeter that has a kind of like an arrow? It's just moved like a 20 volts, 10 volts. What's it called? Tell me. What's that? Is there any specific name for it? For those analog meters that shows even in cars, most of those what is called showing the mileage. These are analog, right? These are analog. Basically, what is it? Is somehow you're converting a speed into a current passing through a tiny bit motors, and that moves that arrow to 70 miles, 50 miles, 60 miles, and whatever the mileage is. So we call that device like an analog meter, and basically is a motor that runs by a current. So I2 is independent. Now, the weird thing here is that R2 does not play any rules, so it's independent of R2. R2 is what is that? It could be big, but the point is the I2 only is a function of the I. It has nothing to do with this. It could be actually a load. I tell you one thing. In circuit modeling 1, you saw, or 2, you saw this symbol. What was that symbol? It's a current source, right? So what does it mean, current source? Meaning what? Excellent. So produces current for any given load. Means the current come out of this one, it doesn't matter. You could connect it to 100K, 10K, 2K, 1K. It doesn't matter. It not depends on the load. It depends on what is internal. The current is always constant, right? Okay. Now, in this circuit, is kind of like this. If you fix VI and fix R1, the current I2 is always constant. If this R2 is a load, it really doesn't matter because always this current passing through is nothing to do with the load. Agree? So this could be a current source. However, I don't like this current source. Why? Because your load, we call this one, your load is floating. Why is the floating? Because it's between two different components. Most of the time, the load, one side is connected to the ground, right? Now, I'm going to introduce this circuit to you. This is also a current source. And we're going to prove it under the specific condition IL is independent of zero. It doesn't matter what load you put it there. The IL is only as a function of the I. Okay, let's do this. Let's prove this and call it a day. Again, these are all a practice of how to analyze the op-amp circuit. I'm using this. What is the I1? If this point is VL, what is that point? VL, right? What is V1? V1 is also VL. So I1 is VI minus IL multiply Z divided by R1, and that has to be, this current has to go through the I2, and your I2 is ILZ minus VO divided by RF. Another equation, I can write I3 has to be IL plus I4. I3 is VO minus IL multiply Z divided by R3 equals, I'm going to keep the IL the same, and I4 is ILZ divided by R2. Combining these equations and factoring out the IL is going to give you IL multiply RF Z divided by R1 multiply R3 minus 1 minus ZL divided by R2 equals VI multiply RF R1 plus R2 Now, under this condition, if RF divided by R1 multiply R3 be chosen equal R2, which is not a big deal, you can pick RF, R1, and R2 to make this equation correct. Then what you have is, you have IL minus VI multiply RF, R1, R3. And of course, if you choose that one, this is minus VI divided by R2. In final equation, do you see any Z or ZL or load? No. The current, that the trick is this part of it. This part is very important. If you choose that part, your output current is only a function of input voltage, nothing to do with your load. That's the current source. So for example, if you choose the VI to be 5 volts and pick those numbers to correct, you always have a constant volt current going through that load. You change the load, still the voltage is going to be constant. Any question? Okay, I'm going to stop here. If you have any questions, stop by. No homework. I won't be here tomorrow. No lab tomorrow. Have a good weekend. Oh, take the quiz. Take the quiz today, 5 p.m., just for your practice. Homework? No. Every single, let's go up. Okay, the question is where to find the homework. If any lecture you look at, it is 9.19, 25, 45, 51. And these are the reading sections. Yeah. I'm your advisor. Which course is it?
I'm doing something with Dr. Boyle.
Awesome. Good luck. Not this week. No, nothing. You have nothing this week due to the drop. Yes. For your own practice, yes. Not this week. Can see, not this week yet. Any question from the census students? Okay. Thank you, and let me know if you have any questions.